Hello, I'd like to talk to you over the next 10 minutes about chemical weathering in New Guinea and its impact on global climate through the reduction of atmospheric CO2, an important greenhouse gas. We know that chemical weathering of mountains can be important in controlling global climate, and this is a model that was developed first in Asia, related to the uplift of the Tibetan Plateau and Himalayas. And the idea was that silicate weathering would remove CO2 from the atmosphere, and therefore if we had a understanding of the intensity of chemical weathering through measuring sediment compositions in the marginal seas around Asia and then coupled that with the regional seismic profiles, we could make an estimate of the amount of CO2 that was being consumed. Using an equation like this, such as was proposed by Christian-Francois Lenord and Lou Derry in 1997, it's possible to try and estimate the impact that might have on global CO2 budgets. And in particular, what we're looking at is the change in calcium, magnesium, potassium and sodium between the source rocks, the original basement source rocks, and the sediment composition that we sample in the deep water submarine fans around Asia. And that was attempted in a study that was done a couple of years ago that looked at drilling data in the Arabian Sea and the South China Sea. Unfortunately, it wasn't possible to do this in the Bay of Bengal because of a lack of a reliable mass flux budget. But in these other basins, what we see is a decreasing amounts of chemical weathering. Say here in the South China Sea, you can see less and less weathering intensity. Likewise in the Arabian Sea, and then a relatively flat profile here in the Mekong. And using oil industry derived seismic, we can make a mass flux budget, a sedimentation budget for all of these areas that allows us to try and estimate the chemical weathering and therefore the CO2 consumption in each of these catchments. The result was that we saw that the Indus was the most powerful influence, not only because of its large size, but also because of its reactive source regions, in which the mafic-rich units of places like Khorestan turned out to be important and making the region particularly efficient in terms of CO2 consumption. And it's interesting to note, therefore, that although the long-term trend in CO2 consumption in the Mekong and the Pearl were quite flat, we saw a decrease in chemical weathering flux and therefore in CO2 consumption in the Indus, which is the opposite of what we would expect if the long-term cooling in the Neogene is to be attributed to uplift and mountain weathering. So if the Himalayas are not the critical feature here, what is? And most recently, myself and my Mohtadi have been wondering about the role that New Guinea plays. New Guinea is a very large mountain belt on a very big island. It's almost as long as the Himalayas, and it's certainly been uplifting rather rapidly since Australia collided with the Indonesian arc around 12 million years ago. So what we see here is that budgets on the modern sediment flux from New Guinea indicate that this may be a very sediment productive region, and potentially, especially given its tropical setting, one that may be actually driving the CO2 budget in a way that we were able to show is not the case in South Asia. The geology of the island of New Guinea is divided between accreted arc units in the north, off-scraped Australian continental rocks here in the south in the front ranges, and then a mobile belt of arc and ophiolite rocks here in the high parts of the Central Highlands. And these mafic rich rocks represent potentially very important and quite weatherable lithologies that would consume a lot of CO2. And certainly we know that the region is undergoing significant erosion. It's certainly a very wet place. There's high rainfall in the center of New Guinea. You can see on this map that the New Guinea precipitation is much greater than what we see in much of South Asia. Moreover, the area is undergoing significant and rapid rock uplift. There is multiple earthquakes that are related to the uplift of the mountains and that also help enhance physical erosion, the products of which then are available for chemical weathering. Where can we look at the long-term evolution of this? Well, there are some drill sites in the deep water Gulf of Papua. What you see down here is DSDP sites 210 and 287 that span a relatively continuous record and presumably mostly derived from erosion of the New Guinea and particularly the Fly River Delta. If you look close to the shore of the Fly River, we see that there are Miocene carbonate units which are overlain by a large prograding clastic delta starting in the Pliocene, at least in this particular place. And so we have confidence that there's been a large amount of erosion and sediment delivery to the Gulf of Papua since that time. Again, looking back at the DSDP sites, they're relatively continuous. The clastic record at 210 appears to go back to the mid-Miocene. It's a more truncated history here at 287, but a Pleistocene record here and a hiatus there on top of Eocene carbonates. So what we did is we've been looking at the weathering history at those sites, and again using major element chemistry to compare mobile with water immobile elements. What we see in potassium aluminum, for example, is a poorly defined trend of falling values from the early Miocene up until the late Miocene, and then a very clear trend here from high to low values starting in the late Miocene. That is more and more chemical weathering, the opposite of what we saw in the Asian submarine fans. A different weathering proxy, rubidium potassium here, shows a similar trend towards decreasing values, so stronger chemical weathering in the Pleistocene. And going along with that, we look at clay minerals, which are also environmentally sensitive. You can see here essentially increasing kaolinite, which is usually associated with stronger degrees of tropical weathering. It's paralleled here, or mirrored, I should say, by the erosion, by a decrease in smectite. Smectite is also usually associated with chemical weathering, but particularly more seasonal and potentially involving the breakdown of volcanic rock, such as we might see in northern New Guinea. So although the kaolinite indicates more tropical weathering, it's possible that some of these trends are related to evolving provenance. We can get a handle on that a little bit by looking at some trace elements. Particularly, you can see here a trend towards increasing zirconium through time, zirconium being particularly rich in continental rocks. So this would suggest an increasing flux of erosion from off-scraped Australian continental rocks, and likewise falling degrees of nickel versus the immobile aluminum, suggesting decreasing erosion from mafic arc terrains. This is better proxied by isotope work, this work being done at the University of Oldenburg in Germany, where we see a sharp rise in a scatter, but nonetheless a sharp rise in 87, 86 strontium values since around 8 million years ago, and that's going along with a fall in neodymium and epsilon neodymium values that indicate more erosion of Australian continental crust. This followed a period where we saw the opposite trend to higher values, so more erosion from arc and primitive units. But what we see here is essentially, since the collision has begun to uplift the highlands, you can see more and more recycling of Australian crust. This shown nicely on this cross plot where we see neodymium against strontium, and the blue here are our Gulf of Papua samples, which are in an array here between essentially an Australian continental end member over here and various arc and ophiolitic rocks up here. So we see a mixing trend here, which is skewing towards more Australian erosion through time since the late Miocene. So just to wrap up, I hope what I showed you was that erosion and weathering in South and Southeast Asia does not sequester more carbon in the way that Ramo and Ruddiman might have suggested, except maybe in the last 3 million years. but not over the longer time period. In contrast, we see in New Guinea that there is this trend to more and more chemical weathering, especially since around 6 to 8 million years ago, and that this is possibly an important part of drawing down CO2 and encouraging global cooling. Some of these mineral and chemical trends may be related to the increasing continental provenance, with the uplift of off-scraped Australian units since the late Miocene. And if we want to convert this weathering intensity history into a CO2 flux, we now have to integrate this with the seismic data from the Gulf of Papua to derive a total budget. Thank you very much.